Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Ladies and gentlemen, welcome back to another live stream. Okay, let me share the stream in my Discord server. Please join my Discord server so you can get notified of new streams. And you can vote for next streams, and you could also join the VC on Discord. So, okay, let me share the stream. Hold on a second. Okay. And let's go. All right, let's start. Okay, so play camping. I'm gonna start from scratch. So I have actually streamed this game before, but because of full screen it was broken. But right now I'm restreaming it pretty much. So congratulations, you have been abducted. We are testing you. The rules are simple. Build a functional computer or you will be eaten. Good luck. Okay. A signal flows from the input to the output. In the upper left corner, under input, there is a green icon. Click on it to turn the input component off. There you go. Okay, nice. Notice that the output component is turned off. This is because the signal stopped flowing from the input component. Next level. We are very impressed with how well you completed the last test. Yeah, pretty hard test, really. Continue. We have decided you're probably not a plant. Okay, nice. Continue. By the way, I actually have enabled colorblind mode for anyone out there that is colorblind. So hopefully that helps. In this level, the challenge is to... Hello, Theo Paris. How is it going, man? Welcome to the live stream. Long time. In this level, the challenge is to figure out how the Nand component works. Be sure to figure it out before you complete this level, or you will get stuck next level. Close. Okay, so this is the Nand gate. We're gonna create the whole computer from scratch, just from this Nand gate. Like from a Nand gate, we're gonna create all the other logic gates, and from all the other logic gates, we're gonna create the whole computer. Then we're gonna create an assembler, etc, etc. It's pretty crazy stuff. I haven't completed this game yet. I have just until some level, but let's go. All right, so this is a NAND gate. If it gets, so this is basically kind of like the truth table basically. So here, if both inputs are on, well, if both inputs are off, then we don't know what's gonna happen. Well, I mean, we could just, I guess, do like this. Okay, so I'm supposed to actually answer this. All right, cool. So if both inputs are off, then it's on. Okay, now what about this one? Let's see. Let's flick this input. Well, it's on. Okay, cool. So it's on. What about, so this off now and this on. So that gives us on. Now the last one is basically both inputs are on, so we're gonna get this output. Cool. Okay, so basically the NAND gate will only be off if both inputs are on. That's basically it. Check. Correct, you have unlocked the NAND gate. With this component you could build everything else in your computer. Close. Let's go. Level NAND gate. This game is very, very underrated, and with other games that I'm gonna hopefully stream next time. But yeah, onwards. Now that you unlocked the NAND gate, it is time for you to build the circuit. Continue. Last level, you made the table that described the circuit. In this level, you build the circuit that matches the table. Okay, so the inverse. Close. Using NAND gates, build the NOT gate. So we only have a NAND gate and we're supposed to build a NOT gate. Okay, close. So here we have the input pin and the output pin, pretty much. Cool. So we're supposed to do something using only the NAND gate to get a NOT gate. Well, let's drop this NAND gate here. So a NOT gate is basically when you have an input, you get the inverse of that input. So for example, if the input is off, no electricity, you get on, which means there is electricity. If you get electricity, then you get nothing back. pretty much, which is the inverse. So this is pretty simple. We're just gonna feed the input to both poles of the NAND gate, the inputs, and then the output, well, to the output, pretty much. Why this is the case? Because if you see here, NAND gate is basically a NOT and an AND gate, right? And yeah, all right, let's run this out. And now we got a NOT gate. We have unlocked the NOT gate just using NAND gate. Cool. Let's go next. Onwards. Great. Let's use keyboard Japan. Nice, cool stuff. Okay, so let's go with the AND gate. Right now, the elephant is dominating all the other test subjects from Earth. Adjusting for brain size, you're also doing well. Continue. Create the circuit that matches the table. Double click on a component to move it together with connected wires. Okay, so here's our truth table now. We need to create an AND gate. So an AND gate is basically on whenever both inputs are on. So this is basically the inverse of a NAND gate, because, you know, like a NAND gate is just not AND, essentially. So what we could do, we could grab our NAND gate here, and basically what we're going to do here, we know that inverting the inverse would just give you back, like, yeah, it would just give you back the input, the original input that you had, right? So like f of f inverse of x, you're just gonna give back x pretty much. So what we could do, we could just bring another NOT gate, so we could cancel the NOT gate with the NOT gate that is inside of the NAND, and there you go. Now we got an AND gate. Pretty much, very simple. Let's go. Run this, and let's go onwards. Now the NOR gate. Most creatures on Earth are aggressive and cannot focus. To succeed, you must learn to think logically while not destroying things. Continue. Create the circuit that matches the table. Double click on a component to move it together with connected wires. Okay, close. Alright, so now we need to create a NOR gate. Well, this is interesting. We're going to use a logic law here. I don't honestly remember what the law is called. If anyone remembers, please let me know. But anyways, let's just do it. So basically a NOR gate is just not OR. And it's basically on only when both inputs are off. Okay, so let's see what we could do. NOR gate. So it's basically, yeah, we need the notch. We're gonna invert both inputs here. Yeah, it's the De Morgan's law. De Morgan's law. That's exactly what we're doing here. Let's check if this works. Oopsies, not this. Okay, did I miss a NOT gate here or something? Yeah, exactly. So that's basically it. So it's an and both inputs are inverted, right? And that's essentially an OR gate. Without, if we wanted an OR gate instead, we will just say not, and here NAND, without this not here. Anyways, onwards, OR gate. Yeah, there you go. Okay, cool. You should be happy you get to participate in our glorious tests. You get a chance to communicate with very advanced people from the galactic civilization. Create a circuit that matches the table. Double click on a component to move it together with connected wires. Interesting. Okay, so we got the OR gate, which is always on except when both inputs are off. Okay, so pretty much we're gonna do the same thing as we've done before, but without inverting the final output. Pretty much simple as that. And let's go. Now we got the OR logic gate. We have unlocked that. Great. Let's go to the next one. Always on. Create a circuit that is always on. There's a lot of ways to go about this, but let's do something very simple. So we got an OR gate, right? And then let's get a NOT gate here. So this is the inverse, and this is going to be the normal input, right? And the input. So like the inverse plus the input itself will always give you 1, you know. It's like it'll always be on, right? So there you go. Let's check it out. And there you go. This level unlocks your first manual page. This one is important. Make sure you understand it. Continue. All right, so this is what I was talking about, De Morgan's laws. The truth tables of the 4 fundamental gates are symmetrical. You can convert between them by inverting the input, vertical arrows, or inverting the output, horizontal arrows, as indicated by the graphic below, right? So you could basically go through this. Okay, notes. You can get from any basic gate to any other. At most, you have to not both inputs and output. You can go between or, nor by inverting output. The same goes and, NAND. In fact, nor means not or, and NAND means not and. Notice the component shape of or, nor are identical except for the little dot at the tip. Pretty much this guy. Yeah. Which means not. And NAND are also identical except for this dot. Negating the output flips all the bits in the last row of the truth table. Negating the inputs mirrors the last row of the truth table around the center. Great. Okay, let's go to the next one. So we got an on and off, basically. Always on, always off. Cool. Great. Let's go to the next one, second tick. Now, this is pretty interesting. As you know, these tests culminate in building a functioning computer. Continue. Species that are capable of finishing are considered sentient by law. This is the main reason we don't eat you afterwards. Output on the second tick only. Output on the second tick only. Basically, the ticks are this. So this is the first tick, this is the second tick, this is the third, this is the fourth. So we have 2 inputs and the desired output, and now we need the current output. Okay, interesting stuff. Second tick. Okay, so basically what we need is that we should only give on when we have the input 1 on, but the input 2 should be off. So you can notice here that this is not symmetric, unlike the previous logic gates, which if you flip the inputs, it wouldn't matter, right? But here, if you flip the inputs, it does matter. Like, it does matter where input 1 goes and where input 2 goes, because they have different results. But let's see how we could do this. Input 1. So let's grab an AND gate, I think, here. And basically what we need is we want it to be on. Hello, gamer Lokiri. Welcome to the live stream. Sorry, I cannot read Russian. So let's say input 1 should be on. Okay, fine. This is input 1, I guess. Let's check, make sure that is input 1. Yeah, it is. Cool. And the input 2, though, should be off. So let's invert this signal. And let's invert the input 2. Notice that the circuit is not symmetric, pretty much. Just like the truth table. So let's run this up, and there you go. Right now, we have made the second tick component. Great. Onwards. XOR gate. Last level, you built a circuit. Equal hello. Okay. I guess it's privyet. I think that's the only word I know in Russian, pretty much. Is that it? I have no clue. Last level, you built a circuit that was on. Yeah, I'm good. Thank you, gamer Lokiri. What about you? Last level, you built a circuit that was on when we were at the second tick. This level, build a circuit that is on when we are at the second or third tick. Interesting. This is also known as an XOR gate. This level is difficult, so don't be discouraged if you don't get the answer right away. Tip, you can connect one output to more than 1 gates. Good to hear, gamer Lokiri. Okay, cool. So now, before what we had is that we should have only gave an on output when we had only input 1 on, and also input 2 should be off. Now you can notice that this one is actually symmetric right now. We output on if this is true or if this is true. Okay, let's start with the circuit that we have done in the previous level, pretty much. So what we have done is basically we got an AND gate and a NOT gate. And that's basically what we had in the previous level of the second tick, right? So there you go. Oh, sorry what I'm doing. This is gonna go to the second input, right? Cool. Yeah, second input. Great. So this is the first one. Now this would actually give us this. This would give us this part of the truth table. But we still need this one though. Hello, welcome to live stream. How is it going? Okay, so let's build the second part of this truth table now. Basically, we're gonna put the same circuit as we've done earlier, right here, but we're gonna invert. So instead of the input 2 being inverted, we're gonna invert the other input, right? The first one, basically, right? Just like that. And like that. You can notice right now, before I said that this was a very not symmetric design, right? But right now when we added this second, like the other side of the puzzle to make XOR gate, right now it's actually symmetric. Look at that. Pretty symmetric. Great. And the same thing as the truth table. It's symmetric. By symmetric, I mean that I don't think this is a technical word. By symmetric, I mean that doesn't matter if you like give the input 1 to input 2 or input 2 to input 1. It doesn't matter which order, you know. So now let's just do this. I'm not sure if we need an OR gate here, but let's see. Okay, a short circuit. We got an OR short circuit. Okay, so let's remove this and make it OR gate here, so we could OR this together. So basically we have this part of the equation and we have this part of the truth table. So we're just gonna add them up together by adding them up in an OR gate. Pretty much, that's it. And let's run this. There you go, we got XOR gate now. Cool. And we got a new entry in the manual: universal gates and truth tables. Onwards, sire. A bigger OR gate, and we got a bigger AND gate. Interesting. Now create an OR gate with 3 inputs. Interesting. We have made an OR gate with 2 inputs before. Let's check the manual though. We have some new entries. Okay, we have truth tables. The tables of inputs and outputs, which are used everywhere throughout the game, are commonly known as truth tables. So we have an AND gate here. This is the truth table of an AND gate. Input and output will often be represented with variable names like in algebra, and instead of using colors, you will often see the values represented as 0, 1, or false and true. And let's go with you. Basically, no electricity, or there is electricity, pretty much. That's how computers work. That's why it's binary, 0 and 1. Universal gates. It turns out that you could build all the logic for a computer out of either NAND or NOR gates. The Apollo guidance computers were built entirely of NOR gates. Well, that's interesting. Designed in the 60s, they had only 4 kilobytes of RAM and 32 kilobytes of disk space, but guided astronauts to the moon nonetheless. And well, today, even using 4 gigabytes, you can't even launch Chrome. Oh well, people have gone to the moon with 4 kilobytes of RAM and 32 kilobytes of disk space. Crazy, man. And only using NOR gates. Not using RTX 3080 or whatever. Just NOR gates, 4 kilobytes of RAM, 32 kilobytes of disk space. Crazy. Just internalize that for a second. Modern computers are built entirely with just one of the universal gates, but when applicable, NAND gates are preferred over NOR because they have less delay and occupy less area. Interesting. So it's just about optimizing space pretty much. Okay. Okay, so that's pretty much it right now. Let's go to the bigger OR gate. Well, now we have all the gates that we have created so far just from NAND gate. Let's try an OR gate right now. Okay, let's see. Well, let's start here. Let's start simple, right? And now there's two ways to go about this. We could either chain the OR gates like this, you know, and there you go. And this would actually work out. And you could chain as much OR gates as you want. Pretty much the same thing as all the other logic gates. They could be chained like this to get more inputs, pretty much. And the other way that you could do this, I think, is by having an OR gate, second OR gate here, I guess, and then, no, this is not applicable to 3 inputs, I believe. Hold on, let me try it. I haven't played this game for a while. But well, you do need another OR gate, I guess, now. Yeah, this is not very optimized, but let's see if it even works. Yeah, it works, right, let's go. So one input goes into both, and the other input's just like that, pretty much. But yeah, I honestly would prefer the other one, which is just to chain them together. It makes much more sense, and it's more optimized, I think. So there you go. Play. Onwards, sire. Let's go. Create an AND gate with 3 inputs. Pretty much the exact same thing as all logic gates. And let's chain another AND gate. So basically, oopsies. Well, basically the output of the first AND gate goes to one of the inputs of the second AND gate. The order doesn't really matter, since the circuits are symmetric, pretty much. The logic is right. Okay, let's run this out. Onwards. Great, so now we're almost done with the basic logic, and we can go to the next level. Create the inverse XOR gate known as XNOR. You can notice here, just like I have said, how many hours do you study in a day normally? Do you mean studying programming? Or what exactly? Sorry, I haven't noticed the message just until now. Create the inverse XOR gate known as XNOR. So you can notice here, just like programming, we have layers of abstraction. So we start with a NAND gate, then we have made a NOT gate, and then we use that NOT gate that we have made, and the NAND gate to create an AND gate, and so on and so on. Yeah, programming CS. I actually don't have really a set amount of hours. I'm just enthusiastic about programming. So like, I don't even count like whatever how much hours it gets, pretty much. So I don't have set hours. Create the inverse XOR gate known as XNOR. It's not very healthy though. It's not very healthy, but yeah. Create the inverse XOR gate known as XNOR. Okay, so the inverse XOR gate should be pretty simple, I believe, unless if I'm missing something. Let's see. There, oopsies, well, there you go. And let's invert this, I guess, and let's see if this works. Okay, pretty simple stuff. And now we have completed the first layer, the basic logic. NAND gate, well, crude awakening. NAND gate, NOT gate, AND gate, NOR gate, OR gate, always on, second tick, XOR, bigger OR gate, bigger AND gate, and finally XNOR gate. Now we're gonna go to the next level, which is arithmetic and memory. All right, right now it's gonna get harder and harder, but hopefully we can do it. Odd number of signals, binary eraser, double trouble. Okay, this level is my favorite pastime, converting decimal into binary under time pressure. Continue. Toggle the bits in the level panel so they add up to the decimal number in the question. You must beat level 3 to pass. Click here to turn on timerless accessibility mode. Okay, ready to race. So basically, numbers, there's like a lot of number systems. There is unary number system, which is just by counting, you know, one by one, rock by rock, or finger by finger. That's unary number system. And are you in bachelor program now? Yeah, what year? Yeah, I'm in bachelor programming, exactly. I'm not sure what year. I guess second year. I don't really count because I'm online pretty much. I just go from one course to the other. So, ready to race. Okay. Though I've skipped a lot of times because I'm pretty much not very like school oriented, I guess. It's like I just do whatever I like, I guess. But anyways, but I need to be more serious about that. But yeah, we have a lot of number systems. We have unary, binary, which is just 0 or 1. So like in unary, you just have 1. 1, 1, 1, 1, 1, 1. In binary, I think you have 0 and 1. In I don't even know what you call it, trinary. But you would have like 0, 1, and 2, pretty much. In this case, in binary, you have just for 0 and 1. So to create numbers in binary, what we do is just this is the powers of 2, because it's a binary number system. So there's 2 possible states, 0 and 1. So you have here 2 to the power of 0, which is 1, 2 to the power of 1, 2, 2 to the power of 2, 4, and so on and on, depending on how much bits you need, right? How much number places you need. This is kind of similar to if you go back to your school days, like primary school or whatever. To learn like the decimal system, which uses 10 numbers, right? 10 digits from 0 to 9. What we were doing is that we were making a table, 1, 10, 100, 1000, and so on. So right now you're just kind of relearning that thing, but with binary this time. It's like just with 0 and 1 instead of from 0 to 9. That's pretty much it. And in decimal system, you have 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and so on and so on. Anyways, let's start the race and see. Level 1, what is 1 in binary? Well, it's just 1. You flip the first bit, pretty much. Now, what is 2 in binary? You flip the second bit. What is 3 in binary? Well, the second and the first bit, and it adds up to 3. What is 13 in binary? Well, let's just go to the biggest one, I guess. And submit. What is 6 in binary? Okay, 4 and 2. So, okay, what is 11 in binary? 11. Okay, submit. Now 12. Submit. What is 1? 14. Submit. What is 22? Well, come on, 21. Come on, submit. What is 2 in binary? Submit. What is 4? There you go. What is 19? Submit. So I'm going through an algorithm. What is 3 in binary? 2. What is 37? Anyways, good job, you reached level 4. But basically, you can notice here that I was going with a kind of like an algorithm to make it very quick. So basically what I was doing, for example, let's say I have 40. What I will do, I will go to the biggest number that is less than 40, which is 32, for example. And then I would keep on flipping until the number is bigger. Then I would cancel that out and go to the next bits, and so on and on. That's at least my own algorithm. You could maybe figure out your own. Good job, you reached level 4. Continue. If you don't know an algorithm, well, it's just basically a series of steps to reach a task. In our case, we just wanted to do this. Anyways, recap. Hopefully you noticed there's exactly one way to write each number in binary. Yeah, it's basically a combination. Right, 2, the value of each digit is always double of the previous digit. Yep, pretty much, because it's a binary system. So like, it's powers of 2. Binary eraser onwards. Great, we have finished that one. Now let's go to the next one, double trouble. Because we are so technologically advanced, we have machines fold our socks. Unfortunately, the circuit that detects sock pairs broke on the machine. Algorithms were studied and documented in the 8th century. Yeah, people were crazy back then. Crazy in a good way. So, okay, cool. Continue. This level has 4 inputs. Output when 2 or more of them are on. So output on when 2 or more of them are on. Well, honestly, I don't really remember how to go with this level. Don't overthink this level. Okay. Pretty good tip right there. I really don't remember honestly this level, but let's see. So. Hold on, go back. Level map manual. Yeah, level log again. Continue. This level has 4 inputs. Output on when 2 or more of them are on. Okay, let's just try it out, I guess. I really don't remember how to pass this level. When 2 or more are on. 2 or more. Maybe XOR gate actually. Isn't it? Well, trying to think here. So XOR gate basically gives us a signal when there is an odd number of input signals that are on. Yeah, pretty much. If there's 2 inputs, like if it's even, so here 2, then it doesn't give a signal, pretty much. If it's 0, it gives a signal, because 0 is even, so at least I guess so. But anyways, let's see what we could do. So if we have this signal on and this signal on, nah, I think it's AND gate probably, yeah, probably. Alright, and let's grab an OR gate. Well, so either this or this. Oopsies. Well. Yeah, I didn't remember how I solved this level, but let's see. Okay, we had it wrong here. Well, I guess maybe I used the XOR gate. Maybe I overthink. Let's see. Let's remove this. Oh well, bruh. Let's see. Anyone have any idea how to solve this? Let's see. 2 inputs are on. Well, we could brute force it, I guess. So either this and this are on, this and this, or this and this. Where's the assignment? The assignment is pretty much because we're so, well, this level has 4 inputs. Output on when 2 or more of them are on. Don't overthink this level. So you have the inner ones and the outer ones. And let's grab an outer OR gate. Let's see if this works. I like to call this the brute force way, but let's see. There may be a better, more elegant solution. But let's see if this even works. Ooh. Well, actually, I see. Because this would be on if one of them are on, which is not exactly what we want, yeah. Okay. You might not need AND gates. Yeah, but let's just see. I honestly forgot how to solve this level. Yeah, well. I really feel like we'll have 2 AND gates and some other XOR gates. That's at least what I kinda remember. It's been a long time since I played this. Well, let's just get the solution. I really don't want to waste more time on this. It's probably something very stupid that I forgot. Alright, yeah. Yeah, it's pretty much the way that I'd like to call a brute force. Yeah, I see. I see now. Well, the level said don't overthink it, but it's actually not that, I mean, well, it's actually simple, but at the same time, it's not that simple. But yeah, let me show you how. Hold on, let me grab the chat back. Where's the chat? Okay, cool. Yo, what's this? Hello, AzanXPL. Welcome to the live stream. How's it going? You could see the description. I have a full description of the game. But basically, you create a computer from a NAND gate, and you keep on creating your own logic gates from there, and you just keep on going to the next abstraction, and finally, you create your own assembler of your CPU. You create your own memory, etc., until you create the whole computer, a whole Turing Complete computer, basically. So you basically create a whole computer from a single NAND gate, pretty much. It's a puzzle game, so you learn how to do that through puzzles, essentially. You have a truth table, and you have to figure out, hopefully, one after the other, pretty much. If you're stuck, you go to the solution and you find out. But yeah, right now I do remember after seeing the solution, I do remember how this actually works, because I haven't played the game for quite some time now. Let me show you how it works. Because the solution, yeah, I did show the solution, but it didn't really explain how it works. So basically, let's just make this a bit more organized, just like in the solution. Oopsies, well, let's put it here. So, just like this. So this is what I like to call the brute force way of doing this, right? So let's put some AND gates. Well, not NAND, AND. Well, how much inputs are on? 1, Ah, I think I see it. Yeah, pretty much no need to explain. Yeah, but some other people need. So one, okay, so desired output. You get 4 inputs fluctuating between 2 states. Basically, you have to use the AND gates to match the. Hold on. Let's see. And you gotta figure out which log gates to use receive. The emoji of YouTube really always hide the comment to use to receive desired output, right? Let's see. Or is it just ands? It's actually not just ands, really. We'll see. I actually can't really remember it even. Let me see the solution again. Come on. Let's see. It's not really the brute force way, actually. Well, kind of, but at the same time, not really. Yeah, so we need 6 AND gates, pretty much. That's a lot of AND gates. Okay. But I remember I did figure this out at some point. But let's just... I think honestly it would be nicer if there was like an easier level before this one, but fine. By the way, I'm not seeing the chat for now. I'm seeing the solution. Hold on a second. Just so we save time. Okay. So here we got the AND gate. Oh well, let's remove this actually. Let's get an AND gate here. Oopsies. Come on. AND gate. Right, and we get the second signal. Let me see the pattern. So the first and the third first. Okay, I see. So if I'm right, then you basically do it like this. 1, 2, 3, 4, 5, 6. Okay. And then you basically say this. So here we said this. Now we're gonna say this one. Then again this. And then this. And now I think we gotta do it like this, if I'm right. Then like this. Then like this. Did you see the pattern here? So let me see if this is correct. I'm not sure, but we'll see how it goes. So now we need some OR gates pretty much. Okay. Let me grab back the chat so I can see your messages. All right, and you gotta figure out. Hold on, you get 4, and you gotta figure out which logic gates used to receive desired output. Right? Yeah, pretty much. If I had like more time, if I wasn't streaming, I would actually sit down and try to solve it myself. But for now, since I don't remember, I don't want to waste time. I just seen the solution because I've already solved this myself before. Just forgot. And you gotta figure out which logic gates used to receive. Yeah, or is it just ands? Yeah, that sounds kind of hard to build Turing Complete computer with just ands. Yeah, just this particular part. Do we need any of 2 inputs to be 1 to solve it? Any 2 of those? Yeah, this is the solution pretty much. Let's get some OR gates here. Okay, you could tell that I don't make Turing Complete computers for a living. I'm just a programmer, but yeah, fine. Let's go ahead and just do it like this. Oopsies. Okay, so you double click pretty much to move this with the pins. And now we just grab another OR gate. Pretty much. And there you go. Let's see if this works. Okay, good. So let me show you right now the pattern. I got it. I remember right now. So basically, we start with this first pin right here for the first one, right? Then for the second one, we keep on going down, okay? So for this is the second pin. Now this will stay the same, and it will stay the same, okay? So first, second, third pin, right? And then finally the fourth pin. Now that we have done with this, like whichever you want to call it, this batch, we go to the next pin in the first one. So it's kind of like binary pretty much. Yeah, it's binary. So you go to the first one. So here, yeah, we're pretty much just brute forcing it. I've seen the solution, but I've actually managed to solve it myself before in previous stream, but I just didn't want to, you know, put more, like waste more time. Anyways, so it's basically the brute force solution. We see all the combinations. So this is the first one, then we just keep on going down, and then we go to the second batch, and then we keep again on going down, then we go to the last one, and there you go. Hopefully you've seen the pattern. If you didn't see it, let me know. I could re-explain it. If you did see the pattern, that's great. And now we check if all of these are on. Well, if one of these are on. If just one of these are on, then we're good. Because if you see here, if just one of these signals is on, well, hold on, how that? Oh no, sorry, the combinations, right? Pretty much. Anyways, whatever. Let's go to the next one. This is kind of a little bit hard, this particular level, but yeah, the game is still in pre-alpha. Anyways, let's go now. Anyways, let's go to the next level. Onwards. So now let's go to odd number of signals. Using a maximum of 3 components, output on, only when an odd number of inputs are on. Yeah, I've actually said this before. We can use an XOR gate. This level has a hint. You can use it if you get stuck. Okay. We needed the hint before in the previous level, not this one. Fine. Let's go with XOR gate. So basically, XOR gate gives a signal. Let me see. So let me show you. So it gives a signal when there's odd numbers of on signals. So here we have one signal on, so it gives a signal. If there is 2, then this is even, so no signal. If both are off, then hold on, what? Yeah, you get no signal pretty much. Okay, so let's actually just basically chain these. Yeah, let's chain another XOR gate. And there you go. Now this would check if all of the signals are odd, like if there is odd number of signals that are on, or if there's no odd, like if there's even odd signals that are on. Run this on, and there you go. The other way that you could do this also is to put XOR gate like this and put another XOR gate here. Then you could do this. Both ways are fine. Both ways are good enough. Oopsies, I forgot this. Okay, play or run. And there you go. Right now we can calculate how much, like, is there odd number of signals or not, pretty much. What do you specialize in your job? High level or rather low level stuff? I pretty much just do programming. I started kinda high level and now I'm drifting towards low level pretty much. Currently my preferred language, programming language, is Rust. It's a low level system programming language. I mean, it's kind of debatable if it's low level or high level, but like generally relative to the other languages, it's low level. And pretty much, yeah. So at first though, I started with Lua, for example, JavaScript, Python and stuff like that, so which is higher level. But then I was more hungry for more control. And then I got more hungry for more control, so I checked out on a course called Nand to Tetris. So you basically create your own computer from a NAND gate, and this is what we're doing right now, pretty much. Circular dependency. In our education system, we traditionally teach by tricking students into doing the wrong thing and then teasing them. Okay. I'm not sure it benefits the students, but teachers love it. Okay. I would love to stay longer, but I got interview tomorrow and I need to refresh some stuff. Goodbye. Thank you for tuning in, and good luck with your interview. Game looks cool though. We'll definitely try. Yeah, it's very, very underrated, and there's a lot of games like this that are underrated that I would hopefully cover in next streams. Creates a circular dependency. This is a circuit where the input of a component relies on its own output. In a circular dependency situation, it is not possible to determine the output of a component because you would first need to determine the input, which relies on the output, and so on, hence the circular. It's like a circular reference if you're coming from a programming background like me. IDK, I don't know if you played Outer Wilds. Definitely. I haven't played it, but I've watched Thor's stream about it, and it's a pretty amazing game. Yeah, it's a very amazing game. Though I don't really have the patience to go through such a puzzle game, honestly. It takes a lot of time and patience. Great experience, but be careful of any spoilers. You can only finish this game once. Hopefully I didn't do any spoilers. Yeah, it's a pretty cool game. If you want to play it, go ahead, and make sure you don't get any spoilers, as Azanex said, or as he mentioned. It's a pretty nice game too. This state is normally not allowed in any other levels, but in this level the goal is to create it, so you understand what it is before going forward. Let's close this and let's go. So, make a circuit where the input of a component depends on its own output. Okay, let's try it. So we have this and we have this, and basically we have this. So, circular dependency. The output of a component leads back to its own input. Though we don't really need this, we could just do it like this. So, basically, we have a short circuit since the component, leads back to itself. It feeds back to itself, so you cannot really, its output is undefined, kind of, but yeah. Creates a circular dependency involving at least two components. Now, I mean, you're not going to make this mistake usually. It's pretty clear, the mistake here, but the problem becomes when you actually have multiple components. Like, let's say you have this, for example. Now, when you have multiple components chained together, it's less clear. You can easily make such a mistake, pretty much. Circular dependency. The output of a component leads back to its own input. Check. And there you go, onwards. Pretty cool. Alright, let's go to the next one. So this basically is for memory. This circular dependency is to create a memory afterwards. And this is for arithmetic, the ALU, pretty much. The ALU components of a CPU. Now, we're gonna make a half adder. We measure the universe with numbers, so your machine must learn to count. Let's go. Continue. Treat the inputs as 0 or 1, depending if they are false, or like off or on. Add them together in binary, such that the result is either 0 or 1. As with normal addition, if the result cannot be described with one digit, set the carry to 1. I need also to wake up early tomorrow. Good luck and thanks for the stream. Thank you for tuning in, and have a good night. Thank you for coming in. As with normal addition, if the results cannot be described. Okay, so this is pretty much just like when you learned addition in primary school. So like you learned to basically add numbers together, like digits together in vertically. And if they don't fit, if you don't have enough numbers, like you reached more than 9, you just carry, you do a carry to the next position, like of the numbers, basically to the next row. Next row? Yeah, next row, actually. Next column of digits, right? Okay, cool. So here we have a sum, and we have a carry. We need to create a half adder, and we have two inputs, basically 2 bits. So, if we have the 2 inputs off, so basically 0 plus 0, you would give 0. But if you have 1 plus 0, you would give 1. If you have 0 plus 1, you would give 1. This is symmetric, kinda, at least in this case. And here we got, if we got 1 and 1, you're going to give desired sum 0. Just like in normal addition, you actually give 0 in the digit, then you carry the 1 to the next column, pretty much. That's exactly the same. So we put 0 in the desired sum, and then 1 in the desired carry. Pretty simple stuff. So this is essentially XOR gate, because, you know, here if you notice, it's basically about odd numbers of signals. Like if you have an odd number of signals, then you go with 1. Otherwise, you go with 0. If it's even, then 0. So for the sum, it's pretty simple. We're just going to go with XOR gate. That's it. Now let's see the carry bit. Well, the carry bit, if you check it out, it's only on when both inputs are on. Is that common? Like, is that relatable? Well, it's basically an AND gate. Just an AND gate, pretty much. And, well, let's do it like this, I guess. Let's see if this works. And there you go. So this is a half adder. The problem though with this adder, why it's called half adder instead of full adder, is that it cannot, like, you know, when you have a carry, but you also have 2 numbers, how do you add these together? Now the half adder cannot really do that. Can only add 2 numbers, not 3 numbers. But in the case when you have an adder, when you have a carry, what you need to do is you need to add 3 numbers, and that's what a full adder is for. And that's why this one is called half adder. So let's go to the next one, pretty much. Counting signals. The output component of this level is a binary counter where the first 3 pins correspond to 1, 2, and 4. Use the binary counter to display the number of signals. Check this hint if you get stuck. The solution for this level is not very neat and requires more components. Oh my gosh. I don't even remember what is the solution. Let's see. The output component of this level is a binary counter where the first 3 pins correspond to 1, 2, and 4. Use the binary counter to display the number of signals. The first 3 pins. Oh yeah, you count the number of signals. Okay. Okay, cool. Desired output. So here we have 1, here we have 1, here we have 2, then here 1, 2, 2, 3, 1, 2, 2, 3, 2, 3, 3, 4. I see. Well, I guess let's go to the other stages first, maybe. Is there anything else? Let's see, there's counting signals, there's delayed line. Let's go with delayed lines for now. This level introduces the delay line component. It takes its input and outputs it 1 tick later. Continue. So 1 tick is like, you know, like in the next tick of the game, if that makes sense. But anyways, construct a circuit that outputs the same as the input, just delayed by 2 ticks. Well, this component is basically to delay the signal by 1 tick, right? So we could delay it by 2 ticks, I guess. Though we don't really need the input, isn't it? Do we? Actually, we do. We are gonna delay it, right? Let's see. Yeah, okay. So basically what's happening here is that you can notice here that here we have off and on, but it's still off, okay? But then after 2 ticks, that happens basically. So you can notice that it's kind of like phased out by 2 ticks. So like here, the 2 is here, but it happened here. The 4 is here, but it happened here. The 1 is here, it happened here. You see, it's kind of like phased out by 2 ticks, pretty much. So that's pretty cool. Let's go to the next stage. Onwards, odd ticks. In the previous level, you learned how we don't allow circular dependencies. Now you must learn the one exception. Learned how we don't allow circle. Okay, cool. Continue. The delay line is allowed to depend on its own input. This is because its input does not influence the rest of the circuit until the next tick. Because this component is delayed, like the output of it is delayed until the next tick, so it doesn't have any influence in the current tick of the input, it's fine to kind of like short circuit it in some sense. Hello 0x Fade, welcome to the live stream. How is it going? Square pins in the game never affect the output in the same tick. They therefore never cause circular dependencies. Continue. Output, and in fact this is very important for memory modules, like we're going to create memory later on. RAM, kind of. Output off on the even ticks and on the odd ticks. Output off on the even ticks and on the odd ticks. Okay, let's see. So we're surely gonna need this guy. And the input doesn't seem to matter, actually. Yeah. So we don't really need it. Is that the case? Let's see. Input. Well, it actually would be always off. Interesting. Well, we could just use always on here to start the circuit, but then what we should do, maybe we need to feed back into it. Oopsies. Huh? Input, desired output, current output. Interesting. Makes sense. Oh yeah, let's see. Alright, I think I got it. So the output is delayed by one tick. Alright, so let's just rotate this by space. And hold on. Let's just see. Yeah, short circuit, of course. Okay, makes sense. Basically, it's supposed to be like this, right? I think. But now, how can we get the input, the first signal? Yeah, let's say, I guess, maybe AND gate. Oopsies, AND gate. You don't need the first signal. Yeah, but, how are we gonna do this? The NOT gate is the first signal. Oh yeah, my bad. I see. Thanks. I forgot about that completely. I actually solved this before, but it just like it's been a long time since. Run. Okay, yeah, makes sense now. So basically what we're doing here is that the NOT gate at first it's on, you know, because it's kind of like inverted, right? So you give the first input, but then that input gets delayed by one tick. So you wait until the next tick, and then basically the NOT gate would get on signal, so the NOT gate would be off. And then it would basically feed the off signal into this guy, and that off signal would basically get kind of affect the circuit in the next tick again, and so on. So what you get at the end of the day is that you get like off, on, off, on, off, on, and so on. Just like that. It's odd ticks, basically. Alright, pretty cool. Onwards. Okay. Thanks 0x Fade for the hint. Let's go. Counting signals. Full adder. Let's try a full adder. In the previous level, we added together 2 inputs. This time we add 3. Once again, add the inputs together in binary such that the result is either 0 or 1. As with the normal addition, if the result cannot be described with 1 digit, set the carry to 1. So as I said before, we have made the half adder. The problem with the half adder is it can only handle 2 inputs, right? But we need another input for the carry too. That's why we have a full adder. Okay, it seems like we cannot use a half adder as a circuit. Okay, let's just recreate it then, fine. So we just need a XOR and an OR gate, pretty much. And another XOR and an AND gate. Great. And now let's see. So this is the half adder. I think, yeah, hold on, no. Actually, we're gonna say, I believe, let's see. Is it really? I don't think actually. Yeah, let's just grab that. Okay, fine. Let's make a half adder first of all. And let's see. Okay. There you go. That's the first one. Actually, maybe it is good. Let's try it. And the carry, well, the carry. We would carry if both, I guess, the sums are on, if I remember. I think so. Let's see. Nah. Done something wrong. So basically I have input 1 and input 2. We add them together. Oh, actually, is it OR gate instead, actually? Maybe it is an OR gate instead. Nah. Well, let's try a half adder then. And we have this. Well, okay, input 1, input 2. Great. Yeah, and let's add another half adder, right? Yeah, I think right now I remember how to do it. Well, actually this goes into, so this is the carry. So I guess maybe this goes here, and this goes here, and essentially this goes here, if I'm right. And well, for the sum, Oh, wow, that's very interesting. No, I think, yeah, I think actually the sum should go here. And XOR. And this would go here, I believe. Is it? Very confused right now. Well. Think of the first output as another carry. Yeah. Yeah, let's redo it. Hold on. Let's make some half adders. I wish if there was half adders here, but anyways. Let's try again. XOR and an AND gate. Okay, so we got this, this, XOR and an AND, right? And now the carry is this guy. So we could hopefully add it together. With this guy. But then, well, this is input 1 and input 2, okay. Well, where's AND gate? Okay. Now we need another AND gate here, which would basically get this input. This. Right. Yeah. No, I meant the output of the first half adder. Yes. So this is the output, right? And this is the actual carry. Okay. Well, there's XOR here. Let's have another AND here. Well, AND. So basically first adder. So the first input goes to here and here, and the second input goes to here and here. Now we have this as a sum, and the carry. Maybe? There you go. Oh, finally. We have created the full adder. Add 3 bits and outputs the sum and the carry. Great. Well, I made this before, but like I completely forgot how to make this. But there you go. So basically we have a half adder here and another half adder here, right? So the first 2 bits, we feed them into the first half adder, and then the output of the first half adder, we feed it into the input of the second half adder, and that's how you get your sum at the end of the day, right? But then you're left off with the carry of the 2 half adders. You just OR them together. If any of them is on, then we just set the carry bit. That's basically it. So yeah, onwards. Alright, that was interesting. Okay, cool. What about a bit inverter here? We're experimenting with how backgrounds influence cognitive functions in Earthlings. Continue. When invert is on, output the opposite of value. Otherwise, just output value as is. Interesting. So it's like 1 minus x, like, yeah, 1 minus t, where t is from 0 to 1, right? So if you give 1, it gives back 0. If you give 0, it gives back 1. Interesting. So like 1, 1, 1. 1, 0, 1. 0, 1, 1. Oh, this is basically XOR gate. Oopsies. Whoa, what the? What about now? Despite the funny background, you figured out this was just XOR gate in disguise. Well done. Let's go. So, bit inverter. Hold on. Yeah, I see. So basically, if you flip one of them, I guess the... Hold on, let me play with it a bit. So... Okay, so this is the invert bit, okay. But I mean, you could do the opposite though. So like here you have a value of 1, right? If you say invert no, then it would just, you know, give that output as it is. So it would give the value as it is. But if you set this invert bit, then it would invert the input, right? So right now instead of 1, it would basically, it would be a NOT gate essentially. Gotta go with you, fun with the game. Thank you, ZeroXFade. Thank you for the hints and have a good day or good night. Thank you for tuning in. So basically, for example, if we want to create, like, let's say a NOT gate, then what we could do is we could just say good night. Then we could just say on and this. This is a NOT gate right now using XOR pretty much. Yeah, so basically XOR gate, it could be used for odd signals and also for bit inverting. That's very cool for inverting a value. Though of course it doesn't matter which order pretty much. Okay, let's go to the next one. Oopsies. Well, let's do this. Alright, let's go to the next one onwards. Okay, right now we have to tackle discounted signals. Okay. So basically, the output component at this level is a binary counter, where the first 3 pins correspond to 1, 2, and 4. Use the binary counter to display the number of signals. Check this hint if you get stuck. 1, 2, and 4. So we have input 1, 2, 3, 4. Oh, hold on a second. If we do, let's say this. Okay, what about, hold on. Yeah, we cannot do this. This is 1, this is 2, this is 4. Interesting. If we combine them, 1 plus 2, 3. 4 plus 2 plus 1, 7. Alright, maybe I got it. So we could say, we could get the 1 through XOR gate. We could, because that basically XOR gate gives us if the signals is odd or not. Because if it's odd, well, for sure there's a 1 in the number, in the binary number. So we could start with that. should be pretty simple to go. All right, let's see. So XOR gate, and another XOR gate here. And this is 1. All right. Now let's check if it's 2. If there is a 2 in the number. If there is a 2. Can I actually run this? Okay, we need the 2 now. So 1 seems to be fine, I guess. For this to be, hold on. The number of signals. Okay, let's maybe try this out. Yes. So well, this is gonna become very spaghetti real quick. So let's do it in another way. Hold on. Let's do it like this. And there you go. Okay, now let's do that first one real quick. So this goes here, this goes here, this goes here, this goes here. And there you go, that's the one. Now for the second. Alt click to move far ahead. Okay, cool. Let's move this more. Cool. Let's go now, maybe try an AND gate here. Maybe another AND gate. Is that really it? Nah. Maybe XOR? Desired output true. Oh, I guess we're missing something. Yeah, we're missing something. Hold on. I got it, I guess. So, well, basically, it would be either these two are on, or these two are on, or these two are on. Basically, the inner ones, or the outer ones. I guess that's basically the case. And basically an OR gate here. Another OR gate to extend it for 4 inputs. Basically a 4 input OR gate. And now hopefully this would be it for the 2. Yeah, let's not waste more time on this. Let's grab the solution. Let's see. Come on, real quick. XOR gate, yeah, for the one we have done it correctly. Great. Ah, I need 6 AND gates. Just like before, yeah. They see. Just like before. And we need some. Oh my god, that's crazy. Sorry, and then we check. Oh yeah, I see. I see. And come on. Oh yeah, I see. Now I understand it. Okay, now I remember. Let's go back. Okay. Great. So we actually need here 6 AND gates, pretty much. Let's actually just redo this part, honestly. So I think for now, this part is pretty much very easy, very understandable. Let's go to the second part, which is detecting 2. So let's see. So we need 6 AND gates. 1, 2, 3, 4, 5, 6. We reached the end. Okay. Can I do this? Okay, cool. Let's grab this guy here. Okay, cool. So we're just gonna do the thing that we have done in an earlier level, which is basically start with the first one, then for the second one, just gonna keep on alternating it. Oopsie, it's not here. So we've done it here, and now here. Same thing here. Now here we're gonna do this. So basically it becomes like this. Now since we have reached the end here, we gotta switch to the second place. So now we're gonna do it like this. And there you go. Finally, you just do it like this. Now this would basically give us, I guess, all the combinations of basically, yeah. And now we're basically gonna check if we have odd signals of this. So let's go to XOR gate. Alrighty, let's grab this here, this here, this here. Oopsies, let's go. And this here. Cool. Nice. Now we just need another, well, actually 2 other XOR gates. Pretty much. One for this guy and one here. Since we have 3 inputs, I'm just going to chain it like this right now. And this is year 2. Crazy. Okay, so that's basically it for 2. 4 though is, well, 4, yeah, it's pretty simple. Like if all of these signals are on, well, there you go, that's 4. So that's pretty simple to do. Well, we don't have enough space left, I guess, but I guess we could, yeah. Like this. Well, actually let's do it like this. Crazy circuit. Okay, cool. So now we're basically just gonna create a big AND gate here. Do we have a big XOR gate? No, we don't. Okay. Alright, so let's go ahead and do this. Oopsies. And now, well, yeah, let's add another AND gate now. Finally. This goes here. Goes here. This is just a big AND gate, like 4 inputs. And this is your 4. And hopefully this is correct. There you go. Okay. So this is we're checking if we have odd signals. This actually we're checking if we have odd signals of all AND combinations. And then here we're checking if all the inputs are on, pretty much for 4. And yeah, that's it for counted signals. Well, that's crazy. And now double the number. Okay, the input and output of this level are used in bytes instead of bits. One of the 2 new components you are given takes a byte and splits it into bits, and the other does the opposite. Using those components, figure out how to double the input number up to 1/27. Well, we know that for each binary position we double, pretty much. So let's first of all split this guy into bits, and let's basically merge it together or join it together using into 1 byte. Yeah. Now, pretty much if we do this, it would be just f of x equal x. Nothing crazy there. Just 1-to-1 mapping. But if we actually, if you're coming from programming background, well, we just basically shift it. Yeah. We shift it 1 bit, and then that's basically multiplication by 2. And that's exactly what we're going to do. We're going to shift by 1 to multiply by 2. So we basically double the number, just like this. Oopsies. And there you go. Let's play this. Level complete. And nice. Now a bit switch. If components output different values on the same wire, you get an error. However, some components have gray output pins. These are not outputting at all when the component is not enabled. This is the case for the bit switch component. When the top pin is off, the output is disabled. When the top pin is off, the output is disabled. This means that more than one of these gray output pins can connect to the same wire and not cause an error as long as only one of them is enabled at a time. I think this is basically like a if condition if you're coming from a programming background. This is the case for the bit switch component. Okay, so it basically either enables the input or disables it entirely depending on this selector bit. I guess, okay. Using 2 NOT gates and 2 switches. Build a XOR gate. Interesting. Okay. So we have 2 switches. Well, it's actually pretty simple. So we're gonna invert 1 input and not invert the other. And here we're just gonna invert one of the selectors, right? Hold on, know what I'm saying. Well, first of all, let's make like an if-else condition in some sense. So this is like a if-else condition, right? Okay, we got some input here. Let's go back to the using 2 NOT gate, build XOR gate. Okay. So let's just same input here and same thing here. Well, this is crazy. Okay, hold on. How we could do this a little bit better. Well, oopsies. Just like that. And here, maybe we're gonna... Actually, it's probably here though. Probably, yeah. But let's see. Oopsies. Well, we could just connect these big... Wow, oh, really? Short circuit? Are you sure? Oh. Oh, I see. Now it's good, okay. Because one output is disabled, the other is not, depending on the selector. And as long as these are, you know, the inverse of the other, it's never gonna short circuit, pretty much. There you go, cool. So just to diode this a bit. So we have, here we're basically inverting the output, right? And here we're inverting the selector and we're just giving the output directly. Yeah, it's basically we're creating a bit inverter. So onwards. Okay, add in bytes, byte not, and byte or. This should be pretty straightforward. You may think it is unethical to eat all the earthlings that don't win the competition. But actually it is okay, because we lived good lives in the wild and we don't let the meat go to waste. Or each bit of the input bytes and the output results. Well, this should be pretty simple. First of all, we split the bytes. And then we make them back again. Now we're just gonna have a OR gate. A lot of OR gates. So this pairwise or together each pair. Okay. So like this. Okay. And another OR gate here. Well, actually, you know what? Just do it like this. Let's do this. So we're basically gonna need 8 OR gates. 1, 2, 3, oopsies. 6, 7, oopsies, 8. Alright, so 4 goes here. Eight. Can we actually do this better? Like, in a more organized way. Well. Maybe? Oh well, anyways, just I guess do it like this. I mean, we could try anyways, fine. Let's try it out, I guess. So it would basically be... Well, actually, let's remove this. And let's put them down there, I guess. So we just have plenty of room. Although we probably don't need all of that room, but let's go. Well, not okay, like this. Alright, cool. Now this would actually get rotated a bit here. There you go. Also this. And let's see. Alright, let's see now. So it's basically well, actually, yeah, we could just do this. Though, honestly, I just figured out that... Oops. Yeah, cool. Great, and now, yeah, we need some OR gates now. Well, like this. First bit here, and so on. So let's make 2, 3, 4, 5, 6, 7, 8. Ooh, that's perfect. Okay. Oopsies. This is the third bit. Actually, is that the case? Hold on. Yeah, pretty much. Third bit. Now the fourth. The fourth. The fifth. Hopefully I didn't miss anything. Sixth. Seventh. Well, what I'm doing. Like this. Like this. And finally, the final one. There, you can see that it's like this in this pattern, kind of. So that's cool. And to even do this. Honestly, no. Come on. Let's go back. Really, that was nicer actually. I bet. Yeah. Alright, so that's basically it now for this one. Let's actually bring this down here. Okay. Yeah, you just do shift. Cool. So let's put this... Alright, let's put it around here, I guess. Yeah. This is 1. This is 2, 4, 8, 16, 32, 64, number 28. And there you go. Nice. And it's pretty nice. OR gate, so 8-bit OR. Why it's... Hold on. Can we make this even nicer? Nah. Yeah, that's actually pretty nice. Yeah, I think this is pretty good. Let's go. Pretty cool stuff. Nice. Alrighty. Onwards. Onwards. Bite not. I mean, come on. Being the main predictor. Our previous model of brain size being the main predictor of intelligence was naive. Tool making and usage is key in the early evolutionary stages of developing intelligence. Therefore, the number of arms on a creature is clearly the main predictor of intelligence. Did you note there are sea creatures from your planet with 4 times as many arms as you, and they are doing better in tests? Yeah, the octopus basically. Continue. Not each bit of the byte input. Again, pretty simple stuff. Just do this. Now we put a whole bunch of NOT gates. And we'll link all of this together. Well, could put this in the center. And there you go. Onwards. Adding bytes. Add the 2 input bytes. Each output bit in the output should be a result of the addition of the corresponding bits from the input and potentially a carry. Continue. If the result does not fit in 8 bits during the output carry, you can think of it as the 9th bit. Finally, there's an input carry as well. This is useful for chain together byte adders to add large numbers. You can think of this carry as adding either 0 or 1. Use this hint if you get stuck. Okay, so we basically have 2 bytes and we need to add them together. We have already, I believe, created the full adder. Yep, there you go. So this adds 3 bits and outputs the sum and the carry. So we gotta use this to add together 2 inputs. Let's see how we can do this. Well, first of all, we need to byte split this guy. Byte split this guy. Pretty much. Now here we have this carry bit, pretty much. Cool. And finally we have byte maker. Why this is a byte? Oh, this is actually 1 bit, right? Cool. So that's basically it. Great. Okay, let's see how we could do this, I guess. Oopsies. Well, actually, oopsies. Maybe we could actually do that little trick to make this a bit more organized. And let's see. So we got this bit. This. Oh, wow. I wonder if there's a faster way to do this. But I guess we don't have to actually even care about this soon after we're done with the 8-bit components or 1 byte components. So there you go. Okay, so now let's make some full adders. Let's use those. We're gonna need, to be honest, I'm not sure how much we're gonna need. Well, let's see. So this is the first bit. Now, the second bit is this. Third bit is this. To be honest, let's just do this. And the next thing actually, oopsies. Oh well, what I've done, bruh. Okay, cool. Now, oh, actually for the next one, we gotta do it like this. So this is the carry. It goes here. And then you basically do, actually, hold on. What about this? Well, let's grab this one for example. You could just say this. Okay, cool. Looking cool. Now let's grab this. Well, actually this should be here, right? Now this second one. And the third. Fourth. Okay, where's that stupid thing? There you go. And let's go. And let's just put these. And there you go. Oopsies. Did I mess up something? Nah, not so far, seems like. Okay. I could tell just from the pattern, pretty much. If something is wrong, I would notice something weird. So that's pretty cool. Let's go to the next one. This. And this. Finally, this. Okay, that's very large. Okay, cool. Otherwise, we could have probably just aligned them, but yeah. Anyways. So, and finally, we have these outputs. Pretty much. Well, actually, that's too big. So yeah, we could put it here actually. And that's the final carry, pretty much. So that's pretty cool. Now let's actually grab these. And our carry is basically this. Hopefully this works. Well. Okay, let's see. Yeah, that seems good to me. Yeah, this is good, pretty much. There you go. And in fact, I only need up to here. Just for organization and style, I guess. There you go. Well, let's see if it works. I mean, the style is nice, but does it work? There you go, nice. Now we got a 8-bit adder. Or a byte adder, pretty cool stuff. Look at that. Nice. Onwards. And negative numbers and input selector. Negative numbers. To know the difference between things in subtraction, to get subtraction first you need negative numbers. This level introduced 2's complement. The most common representation for negative numbers. Here the highest digit is negated. For bytes this means the 8 digits change its value from 128 to minus 128. You finish this level when you get to level 3 or beyond. Click here to turn on timerless accessibility mode. Okay, for bytes this means the 8-digit change. Yeah. Start. What is 1 in binary? Submit. 15. Well, it's basically this. -1, -2, -3, -15, -1, -8. Oh, what I'm doing. Where's -7? -11. -7 again. -15. -19. Okay, there you go. -16. Oopsies. Oh. Well. Anyways. To go between the negative and positive, you flip all the bits and add 1. Yeah, that's why -1 is basically all these bits on in 2's complement. The highest bit is on, the value is always negative. The byte adder you built also works with signed numbers. There's still only exactly one way to write each number. Level complete. Onwards. Signed negator and input selector. Even though it did not pass our test, we decided to keep the dog, and like most Earthlings, he's fluffy and follows simple instruction well. We might want to team you two up since you complement each other's shortcoming well. Input selector. When the bit selector input is off, output byte A, otherwise output byte B. Okay. So we need an inverter. First of all, inverter is basically like this. Not gate here. Okay, let's go. And this would basically go to the output, right? Now here, we need 2 byte splitters. What is this? Oh, the selector, okay. Well, selector would basically go here and finally here. Now here, yeah, we get our, oh, actually I don't need these. It's already like a bit. It's already 1 byte, so there you go. It's as simple as that. Oh, really? Your answer to number 16. Correct answer is 20. Ah, yes, just the other way around basically, so fine. Oh my god, what I've done. Okay, let's put a NOT gate here instead. Come on, bruh. Okay, fine. Let's do this, I guess. Then finally this. And there you go. So that's the byte selector now. So depending on this bit, it selects either this byte or this byte to the output. So we got 8-bit mux. So a byte mixer basically, which is cool. The bus and saving gracefully. Taking the output sign where the 8-bit is -1 or 28. Make a component that takes a number and negates it. For example, 4 negated would become -4, -9 negated would become 9. So yeah, I think I'm too tired at this point to go any further. If you guys like this game, let me know in the comments so I could continue on this one. So for now, what we have done so far is we are almost done with memory and arithmetic. We just have like 4 levels, well 5 levels in memory left and 1 level in arithmetic, but of course the arithmetic level here depends on the memory ones here, but yeah, pretty much. And then hopefully after that we're gonna get to the CPU architecture and then the programming and then the CPU architecture too, then the functions, then the assembly challenges, pretty much. Alrighty. So arithmetic, we need a logic engine, which is basically the ALU, I think. Yeah. Well, not the ALU, it's a part of the ALU. It's for Boolean logic, pretty much. And we need 3-bit decoder, we need a 1-bit decoder, we need a saving bytes, the bus, saving gracefully, sign negator, little box, and counter. Anyway, so that's, and here basically we're gonna get a working computer hopefully. So yeah, that was it for this live stream, and see you later guys. Goodbye everyone.